Question 5. Calculate the enthalpy of combustion kilojoules per mole for alcohol. This is actually not a really difficult question because I've seen questions where it's like 5 marks, enthalpy of combustion, or actually the one that I've started to see the more common than not is appear more commonly is the question where it wants you to find out the temperature change, or it wants you to find out the final temperature, the initial temperature, and you have to find the temperature change and then add it to the initial temperature, subtract from the final temperature, those kind of questions. And those are 5 marks, but in this case, calculate the enthalpy of combustion. Well, we should know delta H is Q divided by moles. Please memorize this. And Q equals MC delta T. That's a classic equation. And all we're going to do to find out delta H, we're going to find Q and we're going to find moles. Well, Q is MC delta T. M is the mass of water. And it gives us a lot of information, but that is the mass of water, 1.250 kilograms. Now, obviously, we want the mass in grams, so it's going to be 250 grams. Kilograms to grams times by 1,000. Pretty simple. So it's going to be Q equals 250 times by C, 4.18, times by temperature change. C is that 4.18 times by temperature change. Temperature change is going to be the difference between the final temperature and initial temperature. 78.1 minus 18.9, 59.2. Q will give me 61,864. Now that's in joules. Q is measured in joules. Obviously, we want enthalpy of combustion in kilojoules per mole to power minus 1, so we do need to divide by 1,000. So I'm just putting that out there, but let's leave that for now. Let's find out the moles. Well, what we're finding out the moles of, well, we're trying to find the enthalpy of combustion for the alcohol, so we're going to find out the moles of alcohol. Does it tell us which alcohol? No, it doesn't tell us what alcohol, so we're just going to say alcohol. The mass of the alcohol. Oh, it's already given us the moles of the alcohol. There we go. So 0.0300. That's why it probably is 3 marks, because it's already given us one of the values. Therefore, delta H equals Q in kilojoules per mole to power minus in kilojoules. So we do need to do 61,864 divided by 1,000. So 61.864 divided by 0.0300. Delta H is Q. In this case, we want in kilojoules divided by number of moles, and that would give me 2,062 kilojoules per mole to power minus 1. Now that is not the final answer, because the temperature tells me quite clearly the temperature of the water increases from 18.9 degrees Celsius to 78.1 degrees Celsius. Therefore, we need to add a negative sign, and we could also say y as temperature increases. So what that tells me? That tells me the reaction is exothermic, and if it's exothermic, we need a negative sign. And then 5.2, table 2 shows the enthalpy of combustion of some alcohols. Explain how your answer to question 5.1 suggested that the alcohol is butanol. So first, we're going to talk about classic statement. Value measured is not accurate due to, well, there's 3 main things that you could talk about, but we only need 1 point, due to heat loss, or you could also say due to incomplete combustion, or you could also say due to the evaporation of alcohol. However, the evaporation of alcohol only works when you're dealing with an alcohol. Some cases it might be a solution or something, I don't know, but yeah, so I'll just say due to heat loss. I'm just showing you guys the variety of options that you could say. But value measured is not accurate due to heat loss. The results from the experiment must be less exothermic than the true value, the real value without the heat loss. So it cannot be propanol or ethanol. Hence must be butanol, because if it's not, we only got 3 alcohols in this table. 2, if it's not going to be ethanol and it's not going to be propanol, then it must be butanol because of the the results from the experiment must be less exothermic than the true value. Minus 2062. Which one is less exothermic than the true value? This one. But these are more exothermic. And then, yeah, it must be less exothermic, therefore must be butanol 1, and ignore just what I just said a bit before that. The 5.3 uses data from table 3 to calculate value for mean carbon-carbon bond enthalpy in pentanol. It's going to take quite a while to do, but we're going to hopefully try to do it as quickly as possible. Delta H, mean bond enthalpy, bond broken, minus bonds formed. So that's the first thing. Knowing the equation, writing the equation down so I know what we're doing. I'm going to find out bond enthalpy of this and subtract it from bonds formed bond enthalpy of this. We also know delta H is minus 3388. Minus 3388. So what are we trying to find? We're trying to find the value for the mean carbon-carbon bond enthalpy. So just one carbon-carbon. So bonds broken. Well, it's going to be CH. You've got CH3, CH2, 3 times CH2, OH. And what I'll do is I'll draw it out and then see how many bonds we're working with, but obviously that'll take quite a while. What we should get is 11 CH bonds, so it's going to be 11 times by 412 plus, well, we've also, think about it, the final part we've got CH2, and then obviously the rest of this, but let's ignore that for now. Then we also got this OH, and now it's going to be O and a H, so therefore you've actually got a CO bond and a OH bond. It's not just an OH bond, and that really tricked me out when the first time I attempted it. So you got a CO and a OH bond, so it's going to be CO, which is 360, and the OH, which is 463. So plus 360 plus 463, and then obviously plus your how many carbons? 1, 2, 3, 1, 2, 3, 4, 5 carbons, so it's going to be plus 4x. Because if you think about it, that's 1, that's 2, that's 3, that's 4 CC bonds. Plus 4x plus just 7.502, 7.5 times by 496. 496 is the O double bond O. Now minus bonds formed. 5 CO2, so it's going to be 10 CO. 10 times by 805 plus 12 times by, because we've got 6 H12, so 6 times by 2 is 12 OHs times by 463. Rearrange it. What I'd do first is add these all up for the bonds broken, and then also add up the bonds formed, and then subtract from each other. And then you should get 4x is equal to 1143, and therefore x is going to be 1143 divided by 4, which give me 286. Let's double check that. 286 times by 4, 24, 32, 40. Yeah, that count. 1143. Divided by 4, you get x is 286. See, positive kilojoules per mole to the power of -1. And at 5.4, calculate the energy density of butan 1R. So in order to do this, we need to find out the moles, and then we need to times it by enthalpy of combustion of butan 1R. So the moles of butan 1R is going to be the mass, but we know it's 0.810 kilojoules per dm minus cubed, and energy density values are measured in kilojoules dm minus cubed, so it's actually going to be 0.810 kilograms is going to be 810 grams times by 1000, so that's going to be the mass divided by mol 74.0. Yeah, that will give me 10.95. Now we want to find out the energy density. All we're going to do to find out the energy density is we're going to do 10.95 times by, we're not going to do times by minus 2676. This minus sign just tells me that it's exothermic, the temperature increases. That's all it really tells me. We don't care about the minus sign, so I'm not going to include it. Times by 2676. So that's obviously in kilojoules multiplied minus 1. That will give me 29,300 kilojoules per dm minus cube energy density. And that's the end of question 5.